Solving in class is probably not the easiest way to solve it. I just like graphing things. I think it's more interesting because I can ask you to graph it and then you can solve it. I'm actually solving for two different things. The much easier method in this one, this is not what I'm doing, but the much easier method would have been a number line with a, let's go ahead. It'd be a -1, it would be a 2, and it would be a 3. This is super easy to do with this one because we just need to know if it's positive or negative in each of these places. So what you could do is just start with a positive, negative, and know it's one of those. And let's pick -2. I'd plug -2 into all of these. And I would say, well, -2 minus 2, well, that's a negative. A negative to the 5th power is negative. 3 minus a -2, that is also, that's going to be a positive. -2 plus 1 would be -1 squared. This one's always going to be a positive. So that would be a negative times a positive times a positive. This would just be negative. You could just pick points here, here, and here, and you could have a very easy time with this. Graphing is probably actually the most difficult way to solve this one, where picking points is much easier because all you have to decide is positive or negative. That being said, I am going to graph it. I'm going to pick the harder of the two methods. Not necessarily harder. It's harder when you're starting out. Like I can just look at that and I know the shape of the graph. But for some of you struggling with evens, odds, what you're looking for, it can be harder to graph. So then just pick points. All right, we need 2 bits of information. We need our zeros. What happens at zeros? So that's an addendum on those 2. And then we also need our leading coefficient or our leading term. Let's handle our zeros first because it's already set up for us. So we didn't actually need synthetic division. That was, I had a different problem there. So we didn't need that. We're going to go ahead and find our zeros. So we have x equals 2. This is actually x equals 3. This is x equals a -1. And then we look at their powers. That is odd. So that means this crosses. This is actually a 1, so it's odd. Crosses. And finally, this is even. And so it's tangent. So the zeros were easy to get in this one. Determining whether they're crossing or tangent was pretty easy too. The hardest part is our leading term or our leading coefficient. To get my leading coefficient, you can go through the whole process of doing x minus 2 to the 5th and then multiplying that by 3 minus x times x plus 1, which would take a really, really long time. Or we can just look directly at our leading coefficient or our leading term. I'm going to go straight to our leading term. To get to my leading term, I'm just going to take all of the x's and multiply them to each other. But first, we look at this first x. That first x is x minus 2 to the 5th, so I need x to the 5th here. I would actually have an x to the 5th. I'd multiply that by my next x, which is -x to the 1st. So I multiply that by -x to the 1st, which is just -x. And finally, we have x plus 1 squared, so I'm going to take out the x squared. So my leading term is going to be -x to the 8th. Knowing that information, I know the end behavior is down and down. So now we can come up with our graph. Let's just put it a little higher. No, I want to skew that way. Our graph crosses at 2, 3, and -1, so I have to go from -1. 1, 2, 3. We have zeros at -1. We have them at 2 and 3. I know I start out low. I go towards that -1. I just have to ask, does it bounce off? Or does it go straight through? Well, we already wrote on there that it's tangent, so it's going to bounce. But it's going to go through the next of them. So it's going to look something like that. Now I just have to ask, when is this less than 0? It's less than 0 anytime it's underneath here. Well, since there's no equal to sign, we're going to use parentheses. So we are going to have from -infinity to -1, union with -1, to 2, union with 3 to infinity. But like I said, the plus minus would probably be the easier way. Plugging in a couple values. All you'd have to do is plug in, 5 values between each one. Actually, 1, 2, 3. You'd plug in 4 numbers, and you'd have all those answers without having to worry about tangent, crossing, leading coefficient tests. It's just plugging in 4 values. Work smarter, not harder. All right? Tests, as we all know, sometimes test isn't how much we know, it's how much we can get done in the time. And working efficiently is the easiest way to get this done. So this would probably be a lot more efficiently if I just came up with a number line, positive, negative, positive, negative. All right, any questions on the bell work? All right, then I'm sure we have one question on the homework at least. And that was the one, number 11. Number 11, and can someone give me what it says, brace 2, or I don't remember what it says.
Brace -1, union, brace negative, or brace 2, union, 3 to infinity. With a bracket on 3.
Yep, 3 to infinity. So we're talking about using inequality to come up with this one. Well, an inequality that has a -1 in it must mean there's a 0 there. It must bounce off at -1. It must also bounce off at 2. And then from 3 to infinity, something has to happen. He either go all the way to infinity, or it has to go all the way to the negative direction. So I'm going to go kind of counter to what I did in my notes. So I'll come up with a slightly different answer because there's a ton of different answers that we could come up with for this one. What I'm going to do on this one, so I'm going to mark where my zeros are. I know there's one at -1. I know there's one at 2. And I know something happens at 3. Well, in order, in an inequality, to get one number out, it has to bounce off at that 0. So what I'm going to try drawing is something that bounces off at -1. Then I have it bounce off at 2. And then I'm going to go up here. Now, for this inequality, I want it to include, let's do it in green. I want it to include that point, and all of this. In order to do that, I need an equal sign. I need it to either be less than or equal to or greater than or equal to so I can include those zeros. Well, let's handle those zeros right off the bat. So we know the function must have zeros at -1, 2, and 3. So let's go ahead and create those. X plus 1, X minus 2, and finally X minus 3. Well, in order for something to bounce off at -1, it must be an even degree. It has to be an even degree. So x plus 1 either needs to be the 2nd, 4th, 6th, 8th. It could be any one of those. I'm going to pick the lower of the values. I'm going to say x to the 2nd to make it bounce off there. It's going to bounce at positive 2, so it's tangent at 2, which also has to be an even power. So I'll make that 2. X minus 3, it crosses straight through it, so it needs to be an odd power. So let's just leave it as 1. You can make it 3, you can make it 5. I don't care what you want to put it as. Well, right now, I have 3 zeros, which is good. I also have, I guess, x squared, x to the 1st, so it's x to the 5th, which means its leading coefficient right now, or leading term, would be x to the 5th plus something, 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 something. It's positive, so yeah, that works. That graph there is a positive odd power because it does go down to the left and up to the right, so that matches. All I need to do is signify that I just want everything up here. So I'm just going to make this greater than or equal to 0. Equal to covers each of these 3 points. Greater than covers that green area there. Does that make more sense? Yes?
I'm kind of confused because in the answer key, the graph is like different.
Uh-huh. I said I'm going to do something that's different than the answer key. But this works too. This is correct too.
Pablo, there's limitless possibilities.
There actually is an infinite number of possibilities. Because I could have did x plus 1 to the 4th. I could have did x plus 1 to the 6th. So in my homework, note what this looks like. I'll copy the one that I did for the answer key so we can see the difference. So I drew a slightly different one. I drew one that started high and went low. But in order to account for that, I put a negative sign out front. And then rather than going greater than or equal to, I did less than or equal to 0. So we could go either direction depending how you drew it or how you thought of it. That's why I wanted to show another counter. Does that make more sense?
Yeah.
Sammy, did you have the same question?
Yeah.
Okay. Both are 100% correct. So if I put that on the test, both, I don't care. Just make sure this, right? That's why I put this negative out front, to account for the fact that it starts up high and goes down low. It has that negative slope. All right, any other questions from the homework? Okay, then let's try to get through this lesson as quickly and painless as possible. We are now in rational functions. This is where things get rough. I do want to talk about, so on your guide for this chapter, we're supposed to have a test on Monday. We're going to move that test to Wednesday. That's going to give us plenty of review time. I'm not here Friday. So Friday, you're just going to get we're done on Thursday. We're done with this whole unit section on Thursday. We have just a few things to get through. Friday, I'm going to give you some practice problems. I won't be here, so it'll just be additional problems for you to work on. Monday, Tuesday, review days. Test on Wednesday. So in reality, you have 3 review days for this test. You have Friday, Monday, Tuesday. All right? This is a complicated section. That's why I made it so short. There's a lot of information we're going to get. And it's primarily with these rational functions. Today is going to start out pretty easy, and then we'll start ramping it up tomorrow and the next day. All right, so we have f of x equals p of x over q of x. What makes this a rational function is if p of x and q of x are polynomials. I also have to put this fact here, and this is a big fact. Q of x cannot equal 0. And why I care so much about that, I'm putting stars by it and everything. This one fact leads us to everything else on this page. This one fact leads us to our domain. And this fact leads us to finding our vertical asymptotes. This one thing is this domain and vertical asymptotes. So the first thing we're going to talk about is the domain. The domain of a rational function is going to be all values except for the ones that make our denominator 0, or q of x 0. So it's all values except for ones that break the function. So we're supposed to find the domain of both of these functions. I just need to figure out where our q of x equals 0. So we are going to set our q of x equal to 0. Well, our q of x is just our denominator, anything that's in the denominator. So we're going to say x minus 1 equals 0. In other words, x equals, not 0, x equals 1. Yes?
Didn't you just say q of x can't equal 0?
I did. So what we're going to add to this now is I'm going to say, I solve for where x equals 1. I'm going to say, don't let it equal that. I'm going to set it equal to 0, find out what makes it 0, and then put on it can't equal that. Because now I can write my domain. Our domain, and probably the easiest way on these is to use bold R, boldface R, which stands for all real numbers, except 1. It's called boldface R. It's not just capital, because notice this extra line here. Maybe if I make it a little bigger and a little neater. It's an R with that. It's the old style of bolding letters, because not everyone used to have computers to bold it for you. So that would be your bold. And math, it's hung around. Boldface R stands for all reals. Just like we had that N for natural, you put an extra thing on that for natural numbers. All right, it's the easiest way to write domain. Our next one, we need to figure out where the denominator equals 0. So I'll say x squared plus 1 equals 0. However, if you're really clever, think about that. What value of x makes that equal 0? Pablo. A negative number would? What's negative 1 squared? No real solutions. There's no real solutions. If I would solve this, I would put a negative 1 here, square root of negative 1. It would be an imaginary number. Since there's no real numbers, we're just going to say there's nothing that can make that 0. That can't be 0. Because Pablo's right. The only thing that would work is if I plugged a negative number in there. Could possibly work. But if I plug a negative number in here, it becomes positive and it becomes bigger. So it can't be 0, so it means our domain doesn't have any restrictions. Our domain is just going to be all real numbers. Or negative infinity to infinity if you want to put it in that kind of notation. There's a reason why I'm putting it like this. Some of these domains get complicated when you have like 3 different vertical asymptotes. And rather than doing negative infinity to a number, to another number, to another number, to negative infinity, it's much easier to say all reals except for and just list the 3 numbers. All right, that's domain. But domain is the exact same thing as your vertical asymptotes. Your vertical asymptotes are those where q of x equals 0. I'm going to put one addition onto that fact. And we're going to get to that in just a second. So I'm going to locate my vertical asymptotes. Vertical asymptotes, exact same thing as our domain. You're going to set your denominator equal to 0. X squared plus 6x plus 5 equals 0. If that is not factorable, as some of you did on the test, don't tell me it's not factorable and quit. We have the quadratic formula. We have completing the square. You have other methods. This happens to be factorable because notes are really nice. They all seem to work out nicely until you get to your homework. But this one is factorable. So we can do x plus 3. No, x plus 5. That makes more sense. X plus 1 equals 0. So right here, to make it 0, we can't, so x can't equal 5. And we can say x can't equal a negative 1. That should have been a negative 5, not a positive 5. If I was asking for domain, you would just say all real numbers except for negative 5 and negative 1. For vertical asymptotes, this is how you have to write them. Vertical asymptotes have to be written as x equals negative 5 and x equals negative 3. It has to be negative 1. I was thinking of a problem that we're doing next. All right. It has to be x equals, otherwise I'll take points off on your test. I am asking for a vertical asymptote. That is a straight line that goes up and down. The only way to come up with a straight up and down line is to have x equals a number. So I don't care what you need to do in your notes. Make sure you know it has to be x equals negative 5. If on the test I ask for your vertical asymptotes and you say negative 5 and negative 1, I'll take off a point. Because you're telling me the point negative 5 is an entire line. Has to be x equals. Has to be. Several will lose points on that one, but that's cool. Those that put in your notes will probably get it right. So make sure you write it as is. All right, the next one says locate your vertical asymptotes. This is kind of an odd duck type problem. If you'd say x equals 3 and x equals negative 1, you actually aren't correct. And why you're not correct is because of this x minus 3 and this x minus 3. we can actually cancel those out. And we could rewrite this as x plus 3 over x plus 1. However, this still affects my function. I still can't plug 3 into my original equation. So because I can cross this out and rewrite it, something else happens here. Because I could cross these out, this is going to be a hole at x equals 3. There's a hole in the graph. That means there's just one point missing. So if you think of like a straight line having a hole, a straight line with a hole would kind of like look like this. You'd put a circle, and then you'd finish the line. We'll talk more about that. We're not going to worry about graphing circles today or holes today. I just want you to be aware of the difference between a hole and a vertical asymptote. So if we can cancel out, it means there's a hole there. But we still do have a vertical asymptote. And we have a vertical asymptote at x equals -1. And it has to be x equals. It can't just be -1. Questions on holes or domain? If I ask you to find the domain or vertical asymptotes, it means the same thing, basically. It's just how you give the answer. The hardest part about rational functions is our horizontal asymptotes. Vertical is pretty easy. You just find where your denominator equals 0. Horizontal, however, we have 3 different cases. One's really hard, one's medium, one's super easy to do. And it all boils down to Bobo Botten eats DC. That's not good enough? You now know how to do it. Just Bobo Botten eats DC. You guys got it? You good?
Yeah.
We're all good? All right, so I can just skip that. All right, let's go right on to graphing these. No, let's cover that. Okay, Bobo Botten eats DC. It is our 3 cases of rational functions. You are going to look at the degree of your numerator and the degree of your denominator. So that's the biggest degree. The biggest degree. So if I have 2x cubed plus 3x squared plus 4x, x cubed is the one I'm looking for. All right, we're looking at our degree of our numerator and denominator. If your degrees are bigger on the bottom, so an example of that might be x cubed plus x squared over x to the 4th plus, I guess, x. We'll just make it crazy. You look at your highest degree. 4 is bigger than 3, so it fits into Bobo. Bobo's got this one. Bobo is the easiest one. This O isn't actually an O. That is actually a 0. And if you ever have Bobo, you just immediately say your horizontal axis is y equals 0. No thought at all. Bobo is always y equals 0. That is your easiest one. Botten is probably the most challenging one. We're not even going to cover it today. We'll cover it tomorrow. Botten means it's bigger on top. So bigger on top might be x to the 4th over x cubed plus 2, something like that. You look at your powers. 4 is bigger than 3. It's bigger on top. That n stands for none. It doesn't have a horizontal asymptote. Sounds like that's nice. However, because we don't have a horizontal one, that typically means you're going to need to find a slant asymptote. And slant asymptotes are the hardest ones. Because a slant asymptote needs an equation, kind of like y equals x plus 1 or something. So this one you're going to actually have to find an equation for. This one's just y equals 0. Easiest one so far. This one we'll learn about tomorrow. The last one, eats DC. Eats DC. That is exponents are the same. So if your exponents are the same, so my example of that might be 3x squared over, I guess, 2x squared plus 7. What you're going to do is you're going to divide the coefficients. So in this case, we have 3 in front and 2 out front, so we're going to have y equals 3 over 2 is going to be our horizontal asymptote. With vertical asymptotes, you have to have x equals. Horizontal, you have to have y equals. And slant will even be y equals. It'll just be y equals an equation. All right, so you have to have those y equals to get your points on those. All right, the next part is we just have to find our vertical and horizontal asymptotes. Well, it's pretty nice because both of these are pretty much the same. Before you get ahead of me, I'm changing B in case you get ahead of me. I'm changing B to be another example with a hole in it. And that is going to be, we're going to change that to quantity x plus 2 times quantity x minus 1 on top over quantity x plus 2 over x minus 3, just so you don't get ahead of me and then have to change it. All right, let's look at A. A has 2x squared and x squared. So we look at the highest powers. That's a 2. That's a 2. They're the same. So we're going to eat DC on this one. That means we're going to divide our coefficients. I'm actually going to first find let's just do our horizontal first. So our horizontal asymptotes is going to be dividing our lead coefficients. Well, in this case, that would be that 2 and that 1 that's in front of there. So this is going to be y equals 2 over 1, which equals 2. In other words, y equals 2 is my horizontal asymptote. I'm also going to go ahead and do the range right off the bat. It doesn't ask for it, but I'm going to do it. Our range is actually going to be all reals except 2. Because 2 is the only place it doesn't exist because we have a horizontal asymptote there. So horizontal asymptotes and range go together. Let's find our vertical asymptote. Because that's where a horizontal asymptote is. We'll see pictures of it. It'll make more sense once we actually see what a picture looks like with these graph. But just picture it's a dashed line that the graph can't go through, but it gets really close to that line, and then it gets really close to the line on the other side.
So wait, what were you doing before that where like you have to make the bottom so like for like the domain or whatever? Oh, so
We'll get to the domain.
all right.
Yep. Our vertical asymptote. Our vertical asymptote is just where our denominator equals 0, so that'd be x squared minus 1 equals 0. This is our vertical asymptote. I would add 1 to both sides, take the square root. We'd have x equals plus or minus 1. You can leave it like that. Just make sure you have an x attached to it. So what that means is our domain would actually be all reals except 1 and negative 1. This is just one example of domain and range. We're going to stop doing it over here. I just wanted to show you how easy it is once you know your horizontal and your vertical asymptote most of the time. On our next one, we're supposed to find our vertical and horizontal asymptotes. So the first thing I'm going to notice is that this 2, x plus 2 and x plus 2 cancel each other out, which means I can rewrite this as just x minus 1 over x minus 3. However, I do have to note there's a hole at x equals negative 2. So once I note that there's a hole, I can rewrite it. Bless you. Bless you. All right, let's go ahead and do our vertical asymptote first. Vertical asymptote, that's just where our denominator equals 0, so I have x minus 3 equals 0. which means x equals 3 is my vertical asymptote. Horizontal asymptote. Horizontal asymptote, we just have to look at the powers. I have x to the first over x to the first. They're the same. We're going to eat DC, which means we divide our coefficients. Our coefficients are 1 and 1. So our horizontal asymptote is y equals 1 over 1, or just 1. Once again, that comes from our coefficients. And that's my vertical asymptote and my horizontal asymptote. Questions on vertical or horizontal asymptotes? The only one that's really hard, that really causes people problems, is this one, but wait till tomorrow to do that. We'll do a whole little blurb about it tomorrow. All right, sketch the graph of g of x equals 3 over x minus 2. State the domain. What we're going to do to graph rational functions is you're going to find your horizontal and vertical asymptotes first. So let's find our vertical asymptote. Our vertical asymptotes where our denominator equals 0, so that's x minus 2 equals 0. In other words, x equals 2. So now we have a vertical line running at x equals 2, and we'll draw that in a second. Let's find our horizontal asymptote first before we draw it. Horizontal asymptote. Our horizontal asymptote either is Bobo-Botten eats DC. It's one of those 3. Which one do you think this one is? Robbie? It is bigger on bottom because, in fact, there's no power on top. There's no x value, so that means this has to be the biggest power. So it's going to be bigger on bottom, so that means we're going Bobo. Bobo is the easiest because Bobo just tells me y equals 0. Let's just graph those, just those 2 lines. So we have an x, y axis. We have to get from, actually we don't have to put any values down yet, so let's just go 1, 2, 3, 4. We'll worry about our values later. 1, 2, 3, 4, 1, 2, 3, 4. Let's go ahead. X equals 2 would be a dashed line right here, and I always do my vertical asymptotes as dashed lines. And we have y equals 0. So these are the worst ones because you can't really show them. But there's my y equals 0. Here's what 99% of these graphs are going to look like. Either we have something in this quadrant that would look something like that, in which case most of the time we'd have something down here. Or we'd have something that's here, which means we'd have something here. That is 99% of these would fall into one of those 2 camps. There's only very rare ones that don't. But just to keep track of just in case it looks a little different, because there are some that kind of look like this and will actually come over here. Just to handle all cases, we are going to pick points from the left of our horizontal and to the right. Not horizontal, our vertical. So we're going to pick points from the left of our vertical and our right of our vertical. So yeah, let's go ahead and put that down. So we're going to plot points. Plot points on either side of the vertical asymptote. So I'm just going to make an XY coordinate system because we can actually plug these in our calculators or figure them out on our own. We have X, Y. I'm going to go ahead and pick my first point to the left because if I can, I always pick 0. If 0 is to the left or right of it, as long as it's not on my vertical asymptote, I'm just going to pick 0. It's the easiest one to plug in. So let's let our X equal 0. If I let my x equal 0, we plug it in here. I'd have 3 over 0 minus 2, which is 3 over negative 2. So it's negative 3 over 2. So we're going to plot that point. 0, negative 3 over 2 would be, let's go ahead and use this, would be about here, which means my graph must look like that. All right, I'm 99% sure that my other one's going to look like this, but let's test a point to make sure it's not that 1% that's weird. So we're just going to pick a value to the right of our vertical asymptote. Looks like 3 would be the first one I would want to pick, so let's pick 3. If I plug 3 in here, we have 3 over 3 minus 2, which is 3 over 1, which is just 3. So we're going to plot the point 3, 3. Which is pretty much how I expected it. We'd come here, we'd go up. So our graphs never cross our, well, most of the time. There are weird graphs out there that cross the horizontal asymptote and do weird things, but most of the time, we're going to know it just gets close, and it just gets close here, gets close up there, and it gets close right there. All right, your homework should not be exceedingly difficult. We start with just basic ones, just like this one that, bless you, that just are, they're going to work. All right, there's nothing funky happening with any of them. Let me just triple check that I didn't pick one that's weird. Nope, they're all pretty easy. Just vertical, horizontal, pick some points to figure out what the graph is. Pablo.
What's the domain?
Shh. The domain for this one, if I asked for the domain, would be from negative infinity. I'm sorry, I went the wrong way. I did the range. But it'd be from negative infinity all the way to 2. Skip 2 to infinity. So it'd be all real numbers except for 2, which goes along with my vertical asymptote. So I guess we could put that right next to it. Our domain would be all reals except 2. And our range would be all reals except 0. So Pablo asked a really great question for those of you not paying attention, because that is a good thing to know about your domain and range, because it will show up. I'm glad you asked that. Other questions? Because I forgot to finish that. I know it doesn't ask for the range, but the range is pretty easy to find. All right, the rest of the time is yours to work.